FreeCAD 1.0 Assembly Workbench. This is the update of the previous version to multi-language version with minor revision. There are 9 languages you can choose from the audio track. Go to Setting and select the audio track of your preferred language. Also, you can enable auto-translate to select your preferred subtitle too. For Chinese version, only subtitle is provided. Select Chinese from the subtitle. I have included the link to download the FreeCAD file in the description if you want to try. FreeCAD 1.0 was released in November 2024 and it came with default assembly workbench. So I give it a try and see what is new in the assembly. The operation is similar to the A2 Plus assembly workbench but with more functions. Like limits and constraints, gear joint, rack and pinion joint and screw joint. I will go through all the functions with simple examples to see how it works. Examples in this video includes linear actuator, bevel gear, spur gear, door closer and more. Hope you find it informative. Let me start now. This part will show how to create a door closer assembly. Create a new file, door closer. In the assembly workbench, click the Create Assembly File icon. Now the assembly is active and the assembly heading is highlighted in yellow. Click the Insert Components icon to insert parts. Then click Open File and go to the directory where I save the parts. Holding the Control key, I can open all the parts files I need or I can do it one by one. Now all the files are inside the window. I select the first component and it will ask me if I want to ground the item. It is same in A2 Plus Workbench, and I need to fix at least one component. So click Yes for now. And I can change it later if needed. And then select the remaining items or I can do it one by one so there will not be too many items at one time. Anyway, this is a simple assembly and I just insert them all at once. Now I can move the parts freely by the mouse. It is a good practice to save the file after I insert items. If I didn't, sometimes, it may not work in creating the joint. Save the file will update the link between files. Select the circular edge on the door and the circular edge at the frame, select Revolute Joint. Use the arrow icon to flip the direction if needed, then click OK. The door can freely rotate. Make it to the 90-degree position. Select the circular edge at the cylinder A and the frame. And create Revolute Joint. Rotate the cylinder to the right. Insert the rod into the cylinder. I can use circular edge or the circular surface to create the cylindrical joint. So the rod can slide and rotate inside the cylinder. Click Cylindrical Joint icon. Use arrow icon to flip it. I can slide the rod now. Select the circular edge at the rod and the door to create Revolute Joint. When I move the door, the cylinder will move correspondingly. Open the tree of the joint. The first, Revolute Joint, is the frame and the door. When I move the door, you can see the values in minimum and maximum are changing. Check the minimum angle and I cannot swing it outward. So this should be the maximum angle. So check the maximum angle and uncheck the minimum angle. Change maximum to -90 degree. Move the door outward and minimum angle is changing. Check the minimum angle and change it to -180 degree. Now the door can be moved within the defined range. This example is the basic operation of assembly in FreeCAD 1.0 with revolute and cylindrical joint. The second part is to create a Scotch-Yoke assembly. Create a new file Scotch-Yoke. In the assembly workbench, create the assembly file. Then insert components. Hold the Control key to select all the files needed, or you can do it one by one. I will to fix the base, so I insert it as the first item to ground it to. Then insert the disc and the yoke. I can move the parts freely except the base, where you see a lock at the base indicating it is grounded or fixed. The first joint is a slider joint. Select the edge of the yoke and the line at the base, click slider joint. The yoke can slide along the base, but no limit is set. Now set up revolute joint for the disc. Select the hole at the disc and the circular edge of the pin, then select revolute joint. Next step, to constrain the yoke to the disc, the pin can only move within the yoke. Select the circular side surface of the pin and the inside surface of the yoke. Then create a distance joint. Set the distance as 0 so two surfaces are touching. When I move the yoke, the disc will rotate. When I rotate the disc, the yoke will slide. The operation is similar to A2 plus Workbench 2. I didn't set up the min-max for the slider. However, the sliding range is limited by the disc and I don't need to define the range. The Scotch-Yoke assembly is done, and let me move to the next one. This part is for Pinion and Rack. Create a new file for Pinion Rack. In the assembly workbench, create the assembly file. Insert components. Open file and go to the directory of parts. Select files needed. Open the first file, which I plan to make it stationary. Select the base. Click Yes to ground the first item automatically. Insert pinion. Insert the rack. Create revolute joint with the base and the spur gear. Select the hole and circular edge of the pin, click revolute joint. Select a line of the rack and the line at the base, then create slider joint. Gears don't mesh. I can either slide the rack or rotate the gear to mesh them. Slide the rack to mesh the gears. The pitch radius of the pinion is 10 mm, the module is 1 mm. So a line 1.25 mm from the root of the rack should meet the pitch circle of the pinion. The base of the rack is 5 mm. So the imaginary line is 6.25 mm from the bottom. So the distance between the pin center and the platform for the rack is 16.25 mm. Select the line at the rack and the hole of the gear to create a joint between slider joint and revolute joint, which come up with the pinion and rack joint. The pitch radius refer to the pitch radius of the gear. In fact, I would say it is half the number of the teeth of the gear. Because with different module, the radius would be different, but the speed ratio of the gear to the rack is still the same. In this example, I use 1 mm for the module, so it is 10 mm or 10 teeth. Move the rack slowly. Now the gear and the rack mesh. We can also set up the min-max for the slider joint, which control the range in the pinion and rack joint eventually. In some case, the rotation direction may be wrong. Open the data window of the pinion and rack joint, change the distance to minus that could reverse the direction. This one is for spur gear. Create a new file. Within the assembly workbench, create the assembly file. Insert component. Open file. Select parts file. Insert the sketch as the first item and make it fixed in position. Beside 3D body, we can insert sketch like use sketch to fix the position of bodies. Then insert 3 gears. Open the sketch and we'll explain the mounting distance between gears. First small gear is 15 teeth, the second one is 40 teeth and the third one is 30 teeth. I use 1 mm as the module, so the pitch diameters are 15 mm, 40 mm, and 30 mm. Mounting distance is the sum of the radius of 2 gears. So the first pair is 27.5 mm and the second pair is 35 mm. Make sure the assembly is active, otherwise all the assembly icon will be gray out. Double-click it or change it to active. I will create revolute joint between the gear and the circle at the sketch. I can select the circular edge at the top or the bottom. Just make sure it is consistent with all 3 gears. Select the bottom edge and the circle at the sketch, click revolute joint. Repeat it for all other 2 gears. All the gears mesh. As gears will be insert with the axis aligned with the axis of the sketch, and sometimes we don't need to adjust the angle. If it doesn't mesh, rotate the gear by half tooth would usually work. That is 180 degree divided by the number of tooth. But in this example, it is good to go to next step. Gear joint is to set up relationship between two revolute joints. So select two revolute joints and define the gear ratio. Select the circle of the first gear and the circle at the second gear, click Gear Joint. For the radius 1 and radius 2, it is to set the gear ratio. So enter the number of tooth of the gear would work. Enter 15 and 40. Repeat it for the second pair. Radius 1 is 40 and radius 2 at 30. It follows the sequence of selecting the gears. If you select the 30 teeth gear first, then you enter 30 for radius 1. Rotate one gear will move all other gears. The color of the gears are not normal and something is wrong. Save the file, close it and reopen it again. The color is okay now. Make sure the assembly is active, otherwise all the assembly icon will be gray out. Double-click it or change it to active. Rotate the gears to test them again. Everything looks good. Spur gear demonstration is done. Gear joint is to relate two revolute joints by the gear ratio, so it should work for bevel gear 2 even the axis of the gears are not parallel. Let me try it out. Create a new file. Create assembly file. Insert components. Open files of components. Insert the sketch first and ground this item. Insert the pinion and gear. The mounting distance of the pinion is 31.12 mm and 20.48 mm for the gear. If you want to find out details of getting the mounting distance of bevel gear, you can see bevel gear assembly 4 animation in my channel. The length of the line is double of the mounting distance as I attach the gear to the center of the line. If the line is same length as the mounting distance, I will attach the gear to the end of the line. Either way is fine. Select the longer line and then select the circular edge of the pinion. Apply revolute joint. Same for the gear. Select circular edge of the gear and then the pinion. Create gear joint. Enter 30 for radius 1 and 15 for radius 2. These are the number of tooth. The gears mesh. Rotate a gear to test it. The direction is wrong. Go to the gear joint. Change distance to -30, which is radius 1. Direction should be correct now, but the gears don't mesh anymore. Go to the first revolute joint, advanced setting. Rotate the angle. Because the gears rotate in wrong direction and I cannot calculate the exact angle to fix it now, and will trial and error to get the correct mesh. Rotate a gear to test it. It looks okay. Hide the sketch and it is done. Belt joint is to relate two revolute joints by the radius ratio, so basically it is same operation as gear joint. Create a new file. Create assembly file. Insert components. Open files of components. Insert the belt first and ground this item. Insert the pulley twice, as I use two same pulleys for the example. As the pulley is a little bit bigger than the belt and the circular edges are not at the same plane, I can select the circular edge and adjust the position based on the dimensions of the belt and pulley. However, I can select the curved surface instead, so the belt will seat right at the middle of the pulley. Select the inside curved surface of the belt, and then select the round surface of the pulley. Apply revolute joint. Do the same for the other pulley. Then select circular edges of two pulleys. Apply belt joint. Enter the value of radius 1 and 2. Rotate one pulley will move other pulley and it animates a belt drive motion. I will create a simple example for ball joint and it is similar to a hexapod. Create a new file. Create assembly file. Insert components. Open file. Select components. Insert the bottom plate first and ground this item. Insert the rod 3 times. Then insert the top plate. Rotate the top plate. Select the ball at the rod and the concave part at the bottom plate. Create ball joint. Do the same for other 2 rods. Then create ball joints for the rod and the top plate. All done. Move the top plate and we can see the movement of the rod. We can use this joint with 6 rods to create a hexapod, something like this. This section is to create a linear actuator. A motor drives a threaded rod which in turn move a block to the desired position. Create a new file. Create assembly file. Insert components. Open file and select the motor and the base. Insert the motor as the first item and ground it. Insert the base. Select the surface of the base and the surface of the motor. Create fixed joint. The base is fixed to somewhere at the center of the motor. Show advanced offsets. Select offset 1 to open the translation tool window. We can use the translation tool to position the base. Adjust the distance at Y to align the base with the motor plate. Then insert the threaded rod. Select the circular edge of the threaded rod and the circular edge of the motor. Create revolute joint so the threaded rod rotates at the motor. Insert the motion block which is thread at the hole. Always select the last item in the body, it is the cut for the motion block. Select the edge of the block and the edge of the base. Create slider joint. The position is good and the threaded rod passes through the motion block at the hole. Insert the support plate. Rotate the support plate. Select the surface of the base and the surface of the support plate. Create fixed joint. The plate is upside down and attached to the middle of the base. We can fix both by using advanced offset. Show advanced offset. Select Offset 1 to open the translation tool window. Change the angle to 180 degree. And adjust distance in Y. Change the color of the block to amber. To create a screw joint, we need to relate the revolute joint and the slider joint. Hide the support plate. Click the block. Go to View. Change transparency to 80. Move the block to match the thread of the rod. Select the block. Change transparency back to 0. Select the line at the block and the circular edge at the threaded rod. Create screw joint. The pitch radius is in fact the pitch of the threaded rod. It is the distance moved when the screw make one complete turn. For M10 thread, the pitch is 1.5 mm. Show the support plate. Move the block and you can see the threaded rod is rotating. Open the slider joint. Move the block and the value in min-max are changing. Move it to the left and check the max length. Then move it to the right and check the min length. So this is the range the block can move. Zoom in the threaded rod and you can see the rotation of the threaded rod. I can rotate the threaded rod to move the block, or move the block to rotate the screw. But in this example, it is easier to move the block to show the interaction between these two components. This section is to demonstrate the distance joint. Create a new file. Create assembly file. Insert components. Open file. Select the block and the plate. Insert the board under the plate and ground this item. Insert the cube under the block twice. Select the edge of the cube and the edge of the board. Create slider joint. Select the edge of the other cube and the edge of the board. Create slider joint. Blocks can slide freely on the board. Select the surface of the cubes. Create distance joint. Enter 6 mm for the distance. Both cubes are jointed and slide together on the board, the distance between them is 6 mm. As in the Scotch-Yoke example, I also use distance joint for round surface and plane. The distance is 0. So they touch each other and slide. This is how distance joint works. I will use the ball joint example to demonstrate the parallel and angle joints in this part. Open the ball joint file which I have deleted the top plate. There are bottom plate and 3 rods. They are still connected by ball joints. Activate the assembly first. Select the rod at the left and then the rod at the middle. Create parallel joint. Now move one joint will move the other rod too. They are parallel all the time. Select the rod at the middle and the rod at the right. Create angle joint. Enter 20 degree for the angle. If I move the rod at the right, other 2 rods will move too. You can see the left one and middle one are parallel and they are at 20 degree with the rod at the right. This is how parallel and angle joints work. This part is to create an perpendicular joint. Create a new file. Create assembly file. Insert components. Open file and select the sketch in the bar. Insert the sketch as the first item and ground it. Insert the bar twice. Select the circle at the sketch and the top circle at the bar. Create revolute joint. Select the circle at the sketch and the bottom circle at the bar. Create revolute joint. Select the edge of the bars. Create perpendicular joint. Move one bar will move the other bar and they are always perpendicular. Some more notes for the offset tool. Open the tree for the joint. Open the revolute joint. Click Show Advanced Offsets. Open offset number 1. We can move or rotate the item after inserting the item. So adjust the values in X, Y, and Z to move the bar. The right-hand column is to select the reference. The item can be moved by the center or by the center of mass. For me, the center should be fine for most applications. Accept the settings and test the joint again. All the joints created before are still valid. Basically, we have gone through all the joints. Let me do a quick review of the bill of materials and exploded view in this last section. I will use the Scotch-Yoke mechanism file as an example. Activate the assembly first. Click the bill of material icon. Open the bill of material. Index is default and I will add the columns I need. Say name, description, and quantity and click OK. Nothing appear. Open the bill of materials again. Add name, description, quantity, and a custom column, material, and click OK. Columns appear now. Open it and export it, but only CVS option is available. I can import CVS file by Excel. Or I just type .xls and save it. Then open the file and save it as Excel. And it is finished. With the exploded view function, click the exploded view icon. Click exploded radially and drag one of the arrow to explode the parts. Then click OK. Go the exploded view at the bottom, open the view to see it again. To explode the parts further, click the part and the transform tool will appear. Move the part to a new position. Select another part, move it and rotate it. Click OK. These steps are stored in the exploded view. Select the view and you see the path and the final position of the part. You can move, rotate, or move it on a plane again. It is basically how the exploded view works in the assembly workbench. Hope you enjoy this video. If you find this video interesting, please subscribe and give it a like. Thank you for watching.